Next, we'll be looking at the effects of pressure and concentration on chemical equilibrium. We're going to be seeing what happens when you increase the pressure and when you decrease pressure in a chemical reaction in an equilibrium system. We are going to see the behavior the system will exhibit when you increase or decrease pressure. And likewise the same for concentration. We're going to see where the equilibrium position will shift to and which reactions, whether the forward or the backward reactions, we're going to see how it's going to be affected. Also remembering that all equilibrium reactions or reactions that involve chemical equilibrium are reversible. So we're going to see what happens in the backward and forward reaction scenarios. Now, for pressure, from what is written here, we see that the effect of pressure is most noticeable when gases are taken into consideration. That is the first one. Now we know that pressure greatly affects the behavior of gases. We are often familiar with terms like compression of gases into certain pressures of, like, let's say 2 atm, or based on units, let's say 800 millimeters of mercury, various pressures. Now we know that pressure greatly affects the behavior of gases, and for chemical equilibrium, we notice the effect of pressure when you take gases into consideration more than when you take liquids and solids into consideration. It's not like pressure doesn't affect liquid and solids, but for this study, and for the most noticeable, the most obvious change in equilibrium, the most obvious shift in the equilibrium position and the reaction that is being favored, we see that it's far easier to notice when you are considering gases than when you are considering liquids or solids. Now, for the second one, when left side number of molecules or number of moles differs from the right side. Now, it is far easier to notice the effect of pressure when you have a forward and backward reaction, a reversible reaction, in which the number of moles on the right side greatly differs than that of the left side. It's far easier to notice the effect of pressure when you have a reaction in which, let's say, in one side you have 4 moles, and then on the other side you have, let's say, 3 or 2, than it is when you are taking into consideration a reaction that has, let's say, just 1 or 2 or let's just, in general, equal number of moles on both sides. So for the reaction we have here, the first reaction we have here, we're going to be looking at the effect of pressure on this reaction and also the effect of pressure on this reaction. Now, for this reaction, the first one here, you see we're going to see the total number of moles for this side and for this side, which is the left side and then the right side. Now, for the left side, you have just 1 mole of nitrogen gas, and then on the left side you have 3 moles. For the reactant, you have 1 mole of nitrogen, and then you have 3 moles of hydrogen, and then on this other side you have 2 moles of ammonia being formed. So, taking that into consideration, you have 1 mole of nitrogen. For hydrogen, you have 3 moles. So 1 plus 3 is 4. So you have total of 4 moles of reactants on this side, and then for the product, you have 2 moles of the product, which is ammonia gas. Now we're going to see how pressure affects this from the basic idea we have written here. Now, from the basic idea we have written here, we see that when high pressure is applied, the reaction involving a decrease in number of moles will be favored, and vice versa. Now, what this idea is all about is when you apply a high pressure on this reaction, which involves a decrease in the number of moles, you can see that from the reactants you have 4 moles, but for the products here you have 2 moles. So what Le Chatelier's principle makes us to understand is that when you apply pressure, when you increase the pressure, when you compress this into a tighter container, into a container of smaller volume in order to increase the pressure, you have a decrease in the number, in order to have a decrease in the number of moles, the reaction will be favored. The forward reaction will be favored when you increase the pressure, on this reaction. So, and also vice versa. So, explaining what happens vice versa, we're going to take a look at this reaction. Now, for this, this isn't balanced, so I have 2. Well, for what you have here, you have 1 mole of this on this side, which is undergoing this reaction, and on this side you have 2 moles. Now, looking at the other side, the reversed scenario, so to speak, which is the vice versa written here, I need to understand that when high pressure now is applied on this reaction, when high pressure is applied this way, instead of the forward reaction being favored, it is the backward reaction that is going to be favored. So for this one now, you have the forward reaction being favored. That means the equilibrium is going to shift to the right side in order to favor the forward reaction. But whereas for this one, you have the equilibrium shifting to this side in order to favor the backward reaction. So that's what happens when you apply the high pressure. Now, what happens when you decrease the pressure, when you lower the pressure, when you put it in the gases in a container of higher volume, so that the molecules can move freely, so they don't amount much energy by colliding with one another and the walls of the container. What happens, in that scenario is that if you lower the pressure for this one, if you lower the pressure for this reaction, the reaction that will involve an increase in the number of molecules will be favored. So when you decrease this, when you decrease the pressure in this particular reaction, the equilibrium is going to shift to this side, to the left side, in order to favor the backward reaction. And for this side, what happens when you decrease the pressure is that the forward reaction is going to be favored. So the equilibrium is going to shift to the right in order to favor the forward reaction taking place. So that's the basic idea of what pressure does, how pressure is a factor that affects the chemical reaction. Taking a look at the scenarios where they are most observable, and then taking a look at what happens generally in the scenarios and the reverse scenarios. Now for concentration, I'm going to be using these examples also to explain that. So for concentration, what we have on the board says when more reactants are added, equilibrium shifts to the right, forward reaction is favored, and vice versa. Now what that means is when you increase the concentration of reactants, the forward reaction is going to be favored. Let's say you have you want to let's say the molar concentration, for example. Let's say the first scenario you have let's say 5 moles per dm cube of the reactant, and then the product, let's say you have 2 moles per dm cube as the concentration of the product. Now, what this is trying to tell us is that when more reactants are added, when you increase the concentration of the reactant, say to like 10 moles per dm cube from 5, what will happen is that the forward reaction is going to be favored, and the equilibrium position is going to shift to the right, and vice versa. So the equilibrium position will shift to the right, which is the side of the product, in order to favor the forward reaction from occurring. It will favor, enhance the forward reaction in order to create a balance. So you won't have more products than reactants, and you won't have more reactants than you have products, and vice versa. So when reactants now are decreased, the equilibrium position is going to shift to the left in order to favor the backward reaction. That is the reversed scenario. So that is the vice versa we're talking about, and that's what basically happens when you have concentration as a factor. When you increase the concentration of the reactants, and when you decrease the concentration of the reactants. So we'll be able to look at what happens in these scenarios.